Good morning or good afternoon, everyone. I'm Chris Spinago from the Warning Decision Train Division. Along with me is Jessica Bunker, also from WDTD. I'd like to welcome you to today's Storm of the Month presentation. Today's presentation comes to you from the Cooperative Institute for Severe and High Impact Weather Research and Operations and the Warning Decision Train Division. Our presenter is Raven Vasquez, who will be giving a presentation titled Looking Back at the 2024 U.S. Tornado Season with Remote Sensing and Reanalysis. With all that being said, Raven, the floor is yours, so go ahead and take it away.
Thank you, Chris. Yes, we're going to be looking back at the 2024 season. We're going to look through a few different lenses. So one by radar, one by Sentinel-2 satellite imagery, and one from RAP Reanalysis grids. This is sort of a follow-up to the November of last year's Storm of the Month, where I presented about Tornado Archive. This is a follow-up to the project where I was detailing a lot of attributes to the 2024 tornado season. So, well, any delay, I'm going to show you some of the preliminary results, and hopefully you guys find this interesting. It's going to be a lot of plots. So this is a reuse slide from the November Storm of the Month. Basically, it details how I'm collecting all this data. So the storm surveys that WFOs perform are key to finding detailed information about the paths and the widths for all these tornadoes. And then once that data is finalized in the NCI storm data, I look through that and try to find errors. So NCI has a spreadsheet with a few other collaborators, and they will contact WFOs asking for if these entries are indeed have errors in it. And then every tornado, like I said, has several attributes. Some about the tornado, if it's a land spout, water spout, mesocyclonic, storm types, satellite, and environmental, and then radar information as well. Here's a little background about the environmental data collection. So every tornado at the very start location and time, it uses the SounderPy package to request the RAP analysis. It's a quarter-degree average box around the tornado start location, and then it rounds to the nearest past hour time. So a 1824Z tornado would be rounded up to 18Z. Those vertical profiles are then sent through the Thunder package. Just in our package has 201 parameters in it. And then some of the parameters dealing with custom storm motions are then found through the SounderR internal packet functions. And then every tornado also include a SKU-T. So there are 2,000 of these that I have saved off somewhere. It's about 1.5 gigabytes of just SKU-T. So a lot of data to look through. So here's a pie chart showing the different tornado types that were in last year's tornado database. These are found by looking at the narrative in SPC filtered reports. It's very handy that these are labeled land spouts in the local storm reports and also in storm data. Now, some of them I had to go dig in NCI to find because they're labeled strong winds and not actually included in the tornado database, but they were documented land spouts. So here we have the majority were mesocyclonic tornadoes, and then a little sliver were land spouts and water spouts. So the process of finding radar attributes is to download the level-II data. For every case, I take the scan before the tornado forms, or full vertical volume scan before a tornado formed, and then all the volume scans through the life cycle, and then one after. And then I look through each one of the scans. At the very start of the tornado life cycle, I classify these storm by its characteristics. If it was, say here, it's a HP supercell, it's in a cluster of storms surrounding it. And I find the motion of the mesocyclone, the first 2 or 3 scans at the beginning of the tornado. And then I find the maximum vrot throughout the life cycle, and at that time also find the mesodiameter, and also if it has a TDS or not. So here we're highlighting a couplet near Hera produced the EF3 tornado. So that methodology follows the paper from Smith et al. 2012. Convective modes for significant severe thunderstorms over the continuous United States. So it's a very subjective classification. There are some automatic, models out there that can perform this, but they don't quite go into the detail that I was looking for. So, and they can often miss like fine radar features that help delineate, say, a line from a line notch or a line break, say, for example. So all these classifications are subjective. Just want to make that clear. So here is a plot of all the storm morphologies over last year's tornadoes. We have pretty good spread of many supercells going over the East Coast. Sort of in the middle, southeast, as expected, you get a lot of QLCS development, especially near Chicago last year. And then as we go further west, you get more of the classic supercells and HP, and then finally disorganized for the land spouts that happen kind of near the Continental Divide. So here's a plot, same plot, just for the supercell submorphologies. So like I highlighted, there's a bunch of mini supercells, basically storms that I found didn't have tops higher than 30,000 feet. You get more of the HP supercells with those darker hues of red. Essentially, they're just really precip-filled RFDs. And then we also do get more of the classic and then LP supercells to go further west with the decrease in moisture. And then here's the same plot for the QLCS morphologies. The majority were line notches, so these kind of aqua colors, very cold pull driven events. Lines are second most prevalent. And then we also get a sprinkling of linear hybrids, which is basically a storm type that isn't quite a discrete supercell, but isn't quite a QLCS. There's kind of a mixture of the two processes occurring. Here's another pie chart with the breakdown. So almost half were supercellular, almost half were QLCS, and the remainder disorganized. And here are the submorphologies of the supercells. So we almost have an even split between classic supercell and HP supercell from last year's tornadoes. LP supercells were very rare to have tornadoes. Of course, this is all subjective in looking at radar, so I don't know how the storm looked in person. So many of these classifications could be in other, submorphologies. But this is a rough idea of the spread of supercells. Here is the same kind of pie chart, but looking at QLCS submorphologies. The majority I found were line notches, so those little tails that kind of curl out ahead of the main line. Some were, or the second most populous was the line where you didn't quite get any features. You got a very sharp gradient between no precip and precip, so we're warning features. And then MCVs and line breaks are fairly rare, only having a couple dozen examples. With all that said, we compared the storm motion with the morphologies, and as expected, storm types that have that are cold pool dominant or forced, rather, they tend to be the faster storm type. So QLCS obviously leads the pack here with a mean motion of about 45 knots. Linear hybrids follow it, HP. What is interesting is that the mini supercells and classic supercells have a pretty decent relationship to each other. They look pretty similar. Of course, we're getting fewer classic supercells, so we're moving matching speed of minis and tropical cyclones. So I mentioned the vrot. This is finding a valid gate of the strongest inbound and outbounds. They're relatively close to where you expect it in storm features. So some of these were kind of ambiguous, like some QLCSs had really broad rotation signatures, so it made it really difficult to find what the vrot actually should be. But this is my best attempt. There is a good overlap between the vrot of QLCS tornadoes versus supercells. So of course, QLCSs are typically weaker, but in the distribution, they fall in line with what you find also in supercell, at least for last year's tornadoes. Looking at the vrot versus its radar distance, there's actually no trend in the data. You could say that closer tornadoes tend to have higher VROTs, which is intuitive, and there's kind of like this slope cutoff. But for the majority of cases, there's really no relationship that I found. The normalized rotation in GR2 analysis also shows a nice relationship with anticyclonic tornadoes being about proportional in intensity to your cyclonic signatures. And then here's a plot showing radar distance and mesocyclone diameter. Each of these lines kind of depicts where the gates are spacing wise. So this is kind of an artificial, I guess, grouping. You can see in the bottom, like 4 or 5 bins here are lines. Regardless, and as expected, supercell tornadic storms typically have a tighter couplet compared to the QLCS. And I wanted to see if there was any sort of relation with the width of the mesocyclone diameter versus surveyed tornadoes, and nope, there really isn't. And then here's kind of a diagram showing how the gates were found based on Thompson et al. 2017. So next, let's look at tornado debris signatures. Here's the CONUS-wide view of which storms or tornadoes produce TDSs. Again, this is still a little subjective, but I looked for areas of 20 dBz or greater in relationship to the storm feature and make sure it made somewhat sense that it was a tornado debris signature. Quite a few tornadoes featured TDSs, especially over the eastern part of the United States. You know, you got more trees and things to loft up than you do over in the high plains or out in the west, where there were very rare occurrences of TDSs. Here's a scatter plot showing the maximum surveyed wind speed and radar distance, and if the tornado produced a TDS. So there's a pretty good relationship. The stronger your tornadoes are and the closer to the radar, you're going to observe a TDS more often. And if your tornadoes are weaker but and farther away, you're likely not going to see one. That's fairly intuitive. And here's a breakdown of tornado debris signatures observed by month. There's an interesting reversal in the pattern you see. You got about even spread or odd that you'll see a TDS in the winter months. As you go into the spring and summer or spring months, we also get larger amounts of tornadoes, but a lot of these are weaker, don't produce TDSs, maybe over more of the pastures and plains of the central United States. As we go into the summer months, tornado activity is relegated to mainly tropical cyclones along the Gulf Coast, where there's lots of twigs and leaves to throw up in the air, and also in the Midwest where you have a lot of crops and farmsteads that are being potentially impacted. Okay, and so what kind of land cover are these TDSs showing up the most over? So most tornadoes occurred over croplands, pasture, and deciduous forest. I would say these are this relationship is more robust than the others. We just simply have more samples. So it's possible that, like, even in developed low intensity categories, if we have more samples, maybe this follows what the other land cover types are. I'll need to investigate that a little bit more with more data. Here's an example of satellite analysis that I conducted. So for every tornado, I looked at the before and after Sentinel-2 imagery to see if there were any apparent scars and how different they were from the ground survey. In that same process, I also rate them subjectively by how apparent the scarring was. So here, Greenfield EF4 last year, that one obviously left a pretty significant scar right through the southeastern portion of that town. Here's Lincoln, Nebraska. So a little different case. It didn't go through much of the town, but you have very apparent ground scarring, so chloridal marks in the path. And then weak is, okay, weak brief tornado over a forested area and knocked down a patch of trees along this pond. So generally these are kind of the features, and after seeing thousands of these, you kind of get a feel of, okay, which signature, you know, is strong, moderate, or weak. So you compare that with the TDS observed, and it shows a very good relationship. Now it's possible this is kind of biased because I was looking at radar before looking at satellite in my workflow. So I kind of perhaps leaned more like, okay, it was TDS with a vrot 70. I'm likely to see moderate scarring. So probably need to do a more objective process for this, but the results here at least show correlation between, okay, so weak ground scarring, half the time you might have a TDS. Got moderate, well, you got way better odds. And then essentially any strong ground signature is going to be throwing debris up in the air high enough that radar is going to be able to see it. Same plot as before, but now for the satellite scarring. So it shows that a lot of the same land type covers also show proportional satellite scarring. What is interesting though is shrub and scrubland has somewhat more moderate signatures. I believe this is skewed from all the EF2 and 3 tornadoes that were found over Texas, kind of like that shrubland area. Not very many forests or things to hit out there. I'm looking at some of the environmental properties. So these, I didn't look through all 215 parameters I had in that in my data set, but some that kind of stood out to me were lapse rates from 0 to 3 kilometers. So there seems to be a cutoff below negative 4 degrees. So you're not having very much low level instability when you got low lapse rates. There's a sweet spot somewhere between -5 and -6 degrees per kilometer that seems to foster most of the tornadic storms, and even some of the the more the stronger tornadoes seem to prefer this general area of lapse rates. And as you get higher up in lapse rates, you get that spread in kind of the opposite direction. So you need to collect more samples, see if this is some relevant pattern here. And then here's a plot for the most unstable parcel, LCL. There's a trend where we have generally lower LCLs, which is very intuitive for stronger tornadoes. Here's a plot that people might be interested in. It's the surveyed maximum wind speed estimated from surveys and then the SCP. So we have two flavors. We have the fixed and the newer version of significant tornado parameter. There's not much of a relationship between SCP and the surveyed winds, at least for the fix. There's a slightly better relationship with the new version of SCP, but still, like some of these, at least from the rat model, and that can have errors. We're getting EF4s and 3s even when we have SCPs of 2 or 4. But we are capturing some of these stronger tornadoes when SCPs are greater than 6. Okay, so kind of going into the last part of this presentation, I have all this data, and it's not easy to plot all these relationships and view them and get, make sense of all of them in a timely manner. So I develop a neural network that I throw everything in. It's not the greatest performing. Obviously, I need to do some feature tuning and maybe some other weighting schemes for these networks. But here I have a neural network estimating tornado wind speeds. I use Optuna to find hyperparameters that perform the best, at least in its little sample of data. So we have 3 layers, and we're using Atom for the optimizer. Once I find the fine-tuned hyperparameters that are performing the best, I also do a 30 seed search to find a model that might be a little more lucky in having lower errors in the training. So it did settle on one of these seeds that has essentially a 40 mile per hour, in either direction spread. And unfortunately, the data is very unbalanced. And that's to be expected. We don't have a lot of significant tornadoes or strong tornadoes. And this just confirms that using 1 year of data it's not going to be efficient. And now what I could do is I have all these EF zeros and ones, which are very well predicted in this model. I can then take some of the weaker EF zeros. So we only have like some 60, 65 mile per hour wind bends here. And say EF2s from other years, just throw that into here so that it becomes a more unified or balanced asset, and then see if that improves this model's prediction. One thing you could do with models is perform a permutation test to find which features the model likes to use in order to create its prediction. For the wind speed model, it found that vrot, storm motion, and if the storm had a TDS, were pretty much all you need to, at least for this model, to predict a tornado wind speed. I did run this model, again, with just environmental features, nothing from radar or the satellite. It shows 600 to 800 millibar lapse rates and 0 to 500 meter lapse rates as being the most important. And tornado intensity, it's still black box. I don't know why I made those predictions, but I can at least find like which features it was keying on, and perhaps there's literature or other scientific like hypothesis for why, or if these environmental parameters actually relate to tornado wind speed. And then next I went with estimating tornado longevity. So same process, find the best hyperparameters, do a 30 seed search. This model did not perform as well as the wind estimate model. So we still have that spread and bias towards longer lived tornadoes, which is to be expected. So same process, I need to find more long lived tornadoes and balance out this data set, which will take a couple years of information. And here we go. Same importance features. So actually keyed on vrot, TDS, and nrot for most important features that were improving the model errors. One that's interesting is that the mixed layer ECAPE actually had a pretty noticeable decrease in the prediction score. So I don't know, again, why the model is choosing that, if there's some sort of reason why that feature is decreasing tornado longevity. I do not know. So that was a lot of talking and a lot of plots. And so I just want to thank you for attending. And if you have any questions, just let me know.
I'd like to thank our speaker, Raven Vasquez, for today's presentation. As always, we are still looking for presenters. So if you have anything you'd like to talk about, please reach out to myself or Jessica Bunker, and we'll get you all signed up. We have nobody in the queue, so the schedule is wide open if there's anything you want to present on. Otherwise, I want to just thank you for attending and hope you have a great rest of your day. Thanks, everyone.